So in this section, we're going to explicitly write out the Feynman rules for quantum electrodynamics, okay? And the magical thing is that this will allow you to basically write down the Lorentz invariant matrix elements if you have this little cheat sheet of rules, okay? I think when I was taking this class, the professor had a closed book test, so I did have to memorize them. But since for this class it's going to be an open book test, you shouldn't try to memorize it, because if you remember one thing wrong, then what happened is that you end up with a really gnarly equation that you can't solve. And actually, in the next chapter, okay, when we deal with electron positron annihilation, there's going to be some tricks that allows you to quickly, right, reduce these complicated integral equations with matrices and 4 vectors in it into something simple, so that you can actually get a number at the end. Okay, so so hopefully I keep you guys motivated through all this math in order for us to get some decent results in chapter 6. Okay, but speaking of gnarly math, right? So remember last section, right? We derive the Lorentz invariant matrix element, okay, which is this huge long equation that has like, I don't know, 1, 2, 3, 4, 5, 6, 7. Let's not count those. 8, 9, 10 different factors in it. And in fact, some of these factors are, right, matrices. Some of them are 4 vectors. Some of them are 4 component spinors. So there's just a huge complication. Some of them you would dot product together. Some of them you will not. Okay. And this describes basically the matrix elements for calculating the scattering of electron of a tau. Essentially, it doesn't even have to be a tau. It, I don't know why the book picked tau, but it, what's below here can be a muon, but it cannot be both be electron, because if it was electron, then they are identical particles. Then you cannot tell the difference between what came out of P3 and P4. So therefore, there will actually be an additional channel to this. So that's why they did, he pick a different particle at least. So it doesn't have to be electrons and taus. It could be electrons, muon, taus, tau, muons, combinations of all these charged leptons. Okay. The reason for the charged leptons is because, neutrino does not interact electromagnetically, so it won't have this diagram at all. Okay. Okay. So, right, this seems like a lot of work, right? What we can do is that, as I think towards the end of last video, what I told you is that there's some pattern here that we're seeing, right? Okay. So let me remind you what this pattern is. Okay. So basically, this whole piece here, right, came from the bottom half of the vertex. Okay. In fact, right, if we were writing this, right, in the forward direction, okay, let's ignore this for now, right? This is what we write first. Okay. We're going to put a circle 1 there, right? But that piece, that factor, right, came from here, right? Is P4. Okay. This middle piece with a nu, right, gamma nu. The reason for it to be gamma nu instead of gamma mu is because you already use mu here, so you can't use the same index twice, right? This piece here, right, I'm going to label that 2, came from the vertex, well, came from the photon here, right, the middle. And then this piece, right, the last piece here, P2, came from the front, right, the incoming particle. So whenever you guys are writing these matrix elements, right, if you write them left to right, you're actually going backward in time, right, in this interaction. Okay, so this is going to be allows us to figure out some pattern, how to just stare at a diagram, follow a few rules, and actually be able to write this down without having to do all the derivation. Okay, and this is the Feynman rules for QED. And then I think if you were reading Griffiths, he basically propped this down. It doesn't tell you where it comes from. It doesn't, so you kind of skip most of chapter 5 and just the last section here. But you won't know why, these rules are the way they are which is one of the reasons why I prefer this book over the other one, even though the notation is a little wonky in this book. Okay, so, but this is just for the T channel scattering, right? So remember, this is the T channel. Okay, so what about S channel? What about the U channel? How do we do anything that's a little bit more complicated? Okay, this is where we're going to find the Feynman rules of quantum electrodynamics, and then essentially you can do all the calculations in quantum electrodynamics to the lowest order diagram. Because as soon as you start adding loops to it, then it gets a little bit more complicated. But we can actually get the lowest order approximation. Basically, the answer is going to be good to 1 in 10,000 because we can actually do this. Okay. So what we want to think about is that, okay, the Lorentz invariant matrix element, which I had a little bit more space, right? So it has some direct spinors, okay, of the incoming and outgoing fermions. Right, I'm going to highlight those up here, right? These little spinner stuff, incoming, outgoing, move it away, okay? Right, this is incoming, this is the outgoing, right? There's this piece here. There's a propagator for the virtual photon, right? Highlight that, highlight this stuff in green. Then the next thing I can do is blue, right? There's this propagator thing, okay? And there's also this vertex factor. Let's do that in yellow, right? Yellow. There's also one more thing I forgot about is the electromagnetic field potential. You don't actually see the potential A mu out right here, but you do see their effect. You do see their effect. Let's do that in magenta, right? In this G mu nu, which is the summation over the different polarization. And you also see this in this gamma mu stuff up here. Okay, so this thing, you can break this stuff apart and then look at it so that we can actually find some rules for figuring out how to deal with each of these components of our Feynman diagrams. Okay, so breaking things up, okay, what you can do is that I'm not even going to read through all of it, but just kind of describe quickly what each of these P's means, right? So you'll have some initial state, okay? The initial state is always going to be the spinor without the adjoint, okay? So let's say I have some, I'm going to draw a very similar diagram, actually exactly the same. So this is P1. So this little piece here, right, this is going to be represented by U's of P, okay? And then there's something going out, right? Let's call that P3, right? Let's say it doesn't change flavor, so it's an electron because QED actually cannot change flavor, so it has to stay the same. Was going to say, so this will be U adjoint of P3, right? So that's how you write this part. Let's deal with the antiparticle stuff in a second, okay? And then this photon here, okay? So it's a photon propagator, so it's not a photon just going out into infinity, okay? So we actually don't do the final or initial state, we actually do the photon propagator. So this piece actually contributes I G mu nu over Q square, okay? And then if we have another particle, let's do muon this time, fancy, right? Okay, we'll call this P2, P4, right? What we do here is we write this as, since it's incoming, it's not the adjoint version, okay, P2. And since this is the outgoing, okay, this will be the adjoint P4, okay? So you want to grab all these different pieces just from reading this diagram, these 5 pieces, okay? And each vertex, okay, this is a vertex, contributes right, I charge of whatever particle we're dealing with, the sign of the charge, okay? I think that's actually not the sub Q, okay? And then this is the elementary charge. Remember, this is either plus or minus 1. This is the 1.6 times 10 to the negative 19 Coulomb. And then you contribute a gamma mu to this, okay? But you get two of these, right? Okay, one for the upper, one for the bottom, okay? In fact, I'm going to write these separately so that it's not confusing. In fact, okay? So this would be the charge sign of the electron, the electric charge, gamma mu. So minus sign here, right? That will contribute to these, the sandwich between these two guys. Okay, the bottom one here is I, Q, tau, has the same elementary electric charge, gamma nu, so that we use a different index, right? This will be sandwiched between these two spinners here. Okay. Okay, so going back to the example we did in the last section, right? Actually, the book actually writes this out for you, but hopefully my little scribbly makes it a little bit more clear where each of the pieces are coming from, right? But just to summarize, right, this comes from the top half of the diagram, okay? This piece comes from the photon propagator, right? This part comes from the bottom half of the diagram, okay? Okay. So this allows you to basically put these little pieces of spinners and gamma matrices and space-time metrics and propagator, right? And then Q is actually equals to P1 minus P3 in this case. These are 4 vectors squared, right? It allows you to calculate all this stuff. And what happened is that, right, if you have any QED vertex, okay, it's going to involve 2 fermion and 1 photon. Okay, why is that? Okay, so even if we have an annihilation, let's say you have an E plus E minus annihilation, which is what we're going to see next. Okay, and this photon just kind of spits out. Okay, you have a photon at a final state, right? This is 2 fermion, 1 photon, right? Okay, there's always going to be 3 particles involved in quantum electrodynamics. Okay, right? And these processes, right, involve these 3 factors, right? The vertex at mu, which is this upper part, the propagator, the middle part, and then the vertex at nu. Okay, we don't have to use the index mu and nu, but you know, if you might as well use it because everybody else does. Okay, and this actually gives you not m, but negative I times m. Okay, which is the Lorentz invariant matrix element. Okay, so let's see how this process goes in annihilation. Okay, so in this case, we actually have to deal with antiparticles also. Okay, so this is the Feynman diagram we're trying to write the matrix elements for. Okay, let's see if we can do that. Okay, so if we apply the Feynman rules, okay, there's 2 vertices. Okay, I'm going to deal with the first vertex first. Makes sense, hopefully. Okay, you have so what we're going to do, I'm going to read this backward. Okay, right, so you have an outgoing particle here. Well, an incoming antiparticle, so it's the same thing as an outgoing particle. Okay, because you should think about the antiparticle as going backwards in time. Okay, okay. A forward-going particle, antiparticle, is the same thing as a regular particle going backward in time. Okay, and that's what these arrows actually indicates, right? Okay, so what I'm going to do is, right, with this anti-electron, right, has a momentum P2. So I'm going to do is, right, well, this is a outgoing, so it's an adjoint to begin with, but this is an antiparticle, so I'm going to do is write the V's instead of the U's, okay? So I'm going to try to write a V, okay? And this will have a form momentum P2. In fact, I'm going to do is write this on the left, so that, because this is horizontal instead. V, P2. Okay, since this is outgoing, we put a little bar on it as an adjoint, okay? running back in time, well, actually following backward from the particle lines, okay, the next thing we see is actually this vertex mu, okay. So in this case, right, following the Feynman rules, okay, any vertex, right, gives you negative q and times the electron, the elementary charge in gamma mu. But what does this mean in this case, okay? Okay, so is this a positive or is this a negative charge? Okay, so for the case of annihilation, okay, we actually just, since we're following the convention where the particle has a negative charge, okay, this will actually be, so I'm just trying to copy that up there, negative I, right, and then Q, big Q in this case is going to be -1 because we're following the particleness of this particular charge. The elementary charge, magnitude, okay, and then we have a gamma mu over here, okay. And then following this back one more time, we end up with the electron, which has a momentum p1, right? And since this is a particle, we use a u, and since this is the incoming particle, we don't do the adjoint. Okay. All right, moving to the middle here, the middle is the same as the other one, where we're just going to get a factor of I g mu nu divided by the form momentum square of the photon. Okay. The outgoing, the other side, the physically outgoing particles, right? This photon decays into 2 muons, okay? It could decay into taus or other things, but let's just deal with this with what the book gave us as a diagram, okay? So once again, okay, what I'm going to do is I'm going to go backward, okay? So, right, we have a outgoing mu minus, okay? So that's a particle, but it's outgoing, so I want the adjoint of this, okay? And this is going to be labeled with momentum 3, okay? And this vertex here, okay, since the particleness is a negative charge, right, once again, we end up with a -1 here, E gamma mu, okay? And then the incoming, well, the particle that's going into the vertex, but it's actually an antiparticle leaving the process, okay? Since this is an antiparticle, I use V instead, okay? And then P4, and since this is a incoming particle, I don't do the adjoint, okay? So, oops, I shouldn't have drawn that, okay? So these are the three factors we're going to deal with, okay? Okay, and hopefully I got this right. The book actually tells you what the answer is supposed to be, okay? So putting all this together, all three of these factors together, right? Let's guide them down here. And then this middle piece, right? Don't forget the little photon propagator, right? Gives you the matrix elements for this particular annihilation process, okay? Well, it's not the matrix element, it's minus I times the matrix element, okay? So that's how you use the Feynman rules to basically write this long equation, okay? And we're going to see how we can actually change this to a number, okay? Which is what the next chapter is going to be about.